2.4, we're going to tie in together the ideas of endothermic and exothermic with what's called a heat capacity and calorimetry. So recall from the 6.1 that the first law of thermodynamics says that the energy of the universe is constant. This means that energy is conserved when we have chemical and physical processes. A big misconception is that the energy will stay in the same form from beginning to end, and that might not be the case. So you might have potential energy in chemical bonds, but then as the reaction takes place, maybe the energy is lost or gained as heat. So there's lots of different types of energy, and we just have to know that all of the types still add together to make sure that energy is conserved. When we are in experiments trying to determine the heat that's associated with a chemical reaction, we use what's called a calorimeter. Calorimetry is the science of measuring heat, and it is based on observing temperature changes when a body absorbs or discharges energy as heat. So we will do a lab where we're actually going to study how the temperature changes affect the amount of heat absorbed or lost, and designing a hand warmer. The heat capacity, usually signified by the letter C of a substance, is a measure of this property defined as it's the heat absorbed over the increase in temperature. Now, the units for this, the heat could be in joules or kilojoules, and the temperature change could be in, so heat is joules or kilojoules. And then the increase in temperature is usually going to be in Celsius, but it could be Kelvin, because the difference in the change of heat between Celsius and Kelvin is just 273.15. So if you subtract Kelvin values or if you subtract Celsius values, it's going to be the same change. Okay? So when an element or a compound is heated, the energy required will depend on the amount of the substance present. So we have things called specific heat capacity, so that we can specify the type of substance that is there or the amount of the substance that is there. So I use C. Sometimes textbooks use S for specific heat capacity, but that has units of joules per gram degree Celsius or joules per Kelvin degree or Kelvin gram. So again, Celsius or Kelvin, interchangeable. 6.1 right here, I have a table of some values of common specific heat capacities. There are more in the textbook, and I will help you find that for your homework problems, or you might just be able to use this table. If the heat capacity is given per mole of the substance, then it's called molar heat capacity, with units of joules per mole degree Celsius or joules per mole Kelvin. So the difference there is grams versus moles. So you have to be careful, which are you given, and then you have to plug in the correct unit for that. So we use simple calorimeters in here, usually just coffee cup calorimeters where there are nested, there's two cups together, as you can see where it says styrofoam cups in this picture, and we use a thermometer to read the temperature, and we have usually a stirring rod in there to help make sure that everything is mixed together. So using this type of calorimeter is an example of constant pressure calorimetry, since the pressure is going to be just the atmospheric pressure, and that will most likely remain constant during the chemical process. So for this constant pressure calorimetry, we have this equation, and the POGIL that we worked on before we started this unit helped us get to this equation, where Q stands for heat, and the heat will usually be in joules when you solve with this equation. Mass will be in grams when you solve for this equation. M is the mass. C is the specific heat capacity, again, sometimes used as S in our textbook, but those units will be joules per gram degree Celsius or the joules per mole degree Celsius, or Kelvin degree instead of degree Celsius, Kelvin. And then the change in temperature will be degree Celsius or Kelvin if you have Kelvin values, but they're the same number interchangeably. Okay. Main difference here is we have to remember that delta H is the change in the heat of the reaction, right? It's the change in enthalpy. And that usually has a unit of kilojoules per mole. So if you're ever solving for the change in enthalpy of the reaction or the heat of the reaction, then you want to, if it's probably going to be a big number, you would like to change it to kilojoules. It's not always required to change it to kilojoules, but it makes those big numbers easier to work with. And usually it's per mole, unless it tells you otherwise, if it says per gram or something. And then the important part is you need to have the sign. Okay, so the sign is going to indicate the direction of heat flow. So when you have a sign, then you have to think about, is it endothermic or is it exothermic? And then you have to think about, how is the problem defining the system and the surroundings? So we'll see that there. But the way that you can use this is you can solve for Q, the heat, and then when you add the sign, then that changes it from Q to the change in enthalpy. And so we'll see an example of that. When 1 liter of 1 molar barium nitrate solution at 25 degrees Celsius is mixed with 1 liter of 1 molar sodium sulfate solution at 25 degrees Celsius in a calorimeter, a white solid barium sulfate forms. And the temperature of the reaction mixture increases to 28.1 degrees Celsius. Assuming that the calorimeter absorbs only a negligible quantity of heat, the specific heat capacity of the solution is 4.18 joules per gram degree Celsius, and the density of the final solution is 1 gram per milliliter. Calculate the change in enthalpy per mole of solid formed. Okay, so we got a lot of information here. All right, so this is a chemical reaction. We are adding barium nitrate to sodium sulfate, and it makes barium sulfate. So just so that we see the reaction we're talking about, let's write that out. Okay, so barium nitrate plus sodium sulfate makes barium sulfate is one product, and then from double replacement reaction writing, we would know that the other products would be sodium nitrate, and we would put a 2 in front to make sure that it's balanced. Okay, but with states of matter, we know both reactants are aqueous solutions. This is a solid, so it's insoluble, and then the sodium sulfate is sodium nitrate is aqueous as well. So for the net ionic equation of what's happening here, we have the barium ions combining with the sulfate ions to form the barium sulfate solid. Okay, so now when this happens, we can figure out Q, because what we want to do first, if we go back to the problem, we want to find the change in enthalpy per mole of the solid formed. Okay, so we need to find, if we're going to be using Q equals MCAT first, so that we can solve for Q and then change it into the heat of the reaction per mole, then we need to make sure that we have all the information we need to plug in. Okay, so I'm going to solve for my Q. That's what I solved for. Okay, now masses. We aren't given any masses. We're given liters. We're given 1 liter of the barium nitrate mixed with 1 liter of the sodium sulfate. We're going to use those to help us find mass, because we know that the density of the solution is 1 gram per milliliter. So this is, if it's the final solution's density, then we have to use the total volume of the entire solution. So total volume would be the 1 liter from the barium nitrate plus the 1 liter from the sodium sulfate, and so that would be a total of 2 liters. Okay, we're not going to just plug in 2 liters though, because the density is 1 gram per milliliter. So to find the mass, what we have to do is we have to take the 2 liters, just set this up like this so you can see, switch it to milliliters, so times by 1,000, or move your decimal 3 times to the right, and then we would multiply by this 1 gram per 1 milliliter. And so that way, that actually gives us 2,000 grams. I'm going to put it in scientific notation. So we have 2,000 grams for the mass, and that came from the total volume of the solution, and we figured that out because we need the density of the solution. Okay, then we still have C and delta T to solve for. So the specific heat capacity, we are given that is 4.18 joules per gram degree Celsius. And then the change in temperature, both of the initial solutions, the reactants, are starting at the same temperature. So that's the initial temperature, T initial. And then when they're mixed together, the mixture raises to 28.1, so that is T final. And so, for finding change in temperature, we always want to take final minus initial. So we have 28.1 minus 25, which is 3.1 degrees Celsius. Okay, so I'm going to plug in the mass, the C, and the change in temperature into the MCAT equation and solve for Q now. Okay, I'm going to switch back over here. So Q is equal to 2,000 times 4.18 times 3.1. So when I solve for that, I got 25,916, and that is in joules. Okay, so we're not done yet because we want to calculate this per mole, and we want the change in enthalpy of the reaction, so we have to think about the sign. Okay, so let's think about how does the temperature change. Okay, what are we actually measuring? Well, these are all solutions, so that means that the reactants are reacting in water, and so the water is actually the surroundings. Okay, so the system is going to be like the barium sulfate, the chemicals, and the surroundings is going to be the water that everything is floating into. Okay, so we are actually measuring the temperature of the surroundings. So if the temperature increased in the surroundings, that means that the heat was flowing to the surroundings. Okay, so if the heat is flowing to the surroundings, then that means that it is an exothermic reaction. So we will need to make it a negative value when we have our change in enthalpy. Okay, and then it needs to be per mole, and this is a big joules value, so I'm going to change it to kilojoules. So you could divide by 1,000 or move it your decimal 3 times left to get it to be kilojoules. So that would be 25.9 kilojoules. And then we're going to make it negative because it's exothermic. Okay, and then per mole is what we need. And if we look back at our balanced equation, there's a coefficient of 1 in front of the barium sulfate. So that'll be 1 mole of barium sulfate. So our enthalpy of the reaction, the heat of reaction, is negative 25.9 kilojoules per mole. So that means for every 1 mole of barium sulfate, 25.9 kilojoules of heat is released. Okay, so how do molar heat capacity and specific heat capacity relate to each other? They're related by molar mass. So I tried to show this here so that you could see how it's related, because if you multiply the specific heat capacity, which is joules per gram degree Celsius, times molar mass, which is grams per mole, then the grams cancel, okay? And so then you're left with joules per mole degree Celsius. So that's how they're related to each other. When we use the MCAT with molar heat capacity, we would replace the mass with N for moles, so that stands for moles. But then our C, we would just have to make sure that we have those units. okay? And then change in temperature would stay the same. So it's the same process with molar heat capacity, but you just have to be careful that you're plugging in moles, not grams, if you have a molar heat capacity unit. So we know that the molar heat capacity of aluminum solid is 24.2 joules per Kelvin mole. Calculate the molar enthalpy change when aluminum is cooled from 128.5 degrees Celsius to 22.6 degrees Celsius. Okay, so we are going to use the MCAT, but we're going to change it to NCAT this time with moles, since it's molar heat capacity that we're dealing with. Okay, and we want to have the molar enthalpy change, so that means we want to know the delta H, so we're going to have to think about the sign when we're done. Okay, so I already know that this is my C for 24.2 joules per mole Kelvin. Now, it doesn't tell me anything about moles. So if it's molar heat capacity, then that's assuming that that is 1 mole. If you're not given moles, then you just assume that there is 1 mole of the substance. Okay? And then temperature, it's cooled from 128.5 to 22.6. So final, let's do this the right way. 22.6 minus initial 128.5 gives me negative 105.9 degrees Celsius change. Now remember, again, Kelvin, degrees Celsius, they're interchangeable because the differences between them would be the same amount. If you wanted to do more work and change them to Kelvin and then subtract, you're more than welcome to, but you'll still get negative 105.9. Okay, so let's solve for Q. So 1 mole times 24.2 times negative 105.9. Now I'm including that negative because that's going to help us figure out the change in enthalpy sign, the molar enthalpy sign. Okay, so when we solve, we get negative 2562.78 joules per mole. And that's because, well, joules really. It would just be joules because the per mole would cancel by multiplying there. Okay. So now I left this sign because I wanted for us to see that, okay, it's going to be an exothermic reaction or exothermic change because the metal is being cooled. So if the metal is being cooled, that means it's losing energy. It's dropping in temperature. So it will be negative because since it is cooled, that means it is an exothermic change. Okay, so we will keep it negative. And then if you want to keep it joules, you can, but for me personally, I would change that to kilojoules. So when I divided by 1,000 and rounded to significant figures, I got negative 2.56 kilojoules. If you would like to put the per mole, you're more than welcome to, but technically it canceled out from our calculation. So the last type of calorimetry we need to talk about is constant volume. So this is when pressure may change but volume does not. And when the volume remains constant, no work is done on the system. So to study the energy changes in reactions where we have constant volume, we use what's called a bomb calorimeter. And so a bomb calorimeter, what it does is it sends an energy pulse through the substance and actually combusts it to completely burn it up. And then you measure the temperature difference of the water outside. So if you see in this picture, the steel bomb, it's not as exciting as what it sounds. I did it in college. But you have water, you have a water tank, and then you put the substance inside of this vessel that you put inside of the water. And so you're measuring the change in the water, so you're measuring the change in the surroundings for the water, and you just press a button and it sends a electric shock through your substance, and then when you open it up, it's all burnt to a crisp when you look at it again. Okay, but so the equation for this is that the energy released is equal to the change in temperature times the capacity of the calorimeter. So when you do constant volume calorimetry, this is for the calorimeter. And so you would have to do some base testing to determine what the calorimeter's capacity is, and then you would use that value then for all of your experiments. So in example 7, we're going to see how that was figured out and used. Oh, this is what it looks like in real life. It's really not that exciting. Okay, example 7. It's been suggested that hydrogen gas obtained by the decomposition of water might be a substitute for natural gas, principally methane. So creating hydrogen gas from water versus burning methane for fuel. To compare the energies of combustion of these fuels, the following experiment was carried out using a Bond calorimeter with a heat capacity of 11.3 kilojoules per degree Celsius. When a 1.5 gram sample of methane was burned with excess oxygen in the calorimeter, the temperature increased by 7.3 degrees Celsius. When a 1.15 gram sample of hydrogen gas was burned with excess oxygen, the temperature increase was 14.3 degrees Celsius. Compare the energies of combustion per gram for hydrogen and methane and see. So what we're going to do is when we compare them, we are going to see, we want to find the same, the energy per gram, and then when we compare them, we'll see is one better than the other. And it would be better if it produces more energy. Okay, so we're given a lot of information, a lot of words here. Our two different substances are methane and hydrogen gas. So methane's formula is CH4 because meth stands for one carbon. And then hydrogen gas. Okay, so back from the words, it told us that we had 1.5 grams of methane used, and when that was burned, the temperature increased by 7.3 degrees. So that would be your change in temperature. Okay, and then for the hydrogen gas, we had 1.15 grams, and then we had a temperature change of 14.3 degrees Celsius. And it tells us that the heat capacity of the Bond calorimeter is 11.3 kilojoules per degree Celsius. So what we're going to do, we're going to do the same calculation for both, where we are going to take, so we'll do the methane first. We're going to take the change in temperature, 7.3 degrees Celsius over 1, and then we're going to multiply it by that specific heat capacity, or not, sorry, just the heat capacity, it's not specific. It's specific to the calorimeter. So times 11.3, and that's kilojoules per degree, 1 degree Celsius. And so that way, the degree Celsius cancel away. Okay, but then we want to compare the energies per gram. So since they had different mass amounts, we are then going to divide by the mass. So I'm just putting 1 as a spot filler to show that we're dividing by the mass of the methane. Okay, so if you multiply across the top, that is 82.49 kilojoules divided by 1.5 grams is 55.0 kilojoules per gram. Okay, so we're going to do the same calculation for the hydrogen gas now, but plugging in that information. So the change in temperature was 14.3 degrees Celsius. We're using the same heat capacity because it was the same calorimeter used. So then that way we can cancel out our degrees Celsius, and then this time we're going to divide by 1.15 grams because that is the grams of the H2. So the top I got 161.59 kilojoules divided by 1.15 grams, and so that is 141 kilojoules per gram. Okay, so let's compare these. Now that we got them, let's compare them. Well, if we look, obviously the hydrogen gas is bigger than the methane gas, so that means that we have more heat released or more energy released from the combustion to make the hydrogen gas. It's actually, if you divide them, if you take 141 divided by 51, it's 55. It's about 2.5 times bigger. So that means that the hydrogen gas has about 2.5 times more energy released. So that means that since it is releasing more, even 2.5 times more, it's a lot more efficient than the methane. So that's why hydrogen gas might be a good alternative if we're looking for greener and renewable resources versus methane or other non-renewable natural gas resources.